Hello, IB. Welcome to Chapter 4. So we're going to go ahead and take a look at Section 4A and 4B, which is all about logarithms in base 10 and in base A. So in other words, applying any base for logarithms. Let's see what a logarithm actually is to begin with. If we take a look at something familiar to us, which is our exponential equation, so 10 to the x power, and I go ahead and find the inverse, so reflecting over the y equals x line, I get a function that is in blue. This blue function is known as my inverse of my exponential function, also known as your log of that same base, so base 10 of x. So I've got my exponential function and the reflection over the y equals x line, which is my logarithmic function. Let's see if that same reflection will prove to be the case if I look at base 2. So if I have y equals 2 to the x, again, if I reflect over that y equals x line to find my inverse, we'll notice that you get log base 2. So you could take any base that you wanted, even our natural exponential e, and I can reflect over the y equals x line, and I should get log base e of x. So if I graph these, this is what I would find, and I would notice that they match up. And we'll do a little bit more of this in class as well. So just coming down to the basics, when you have an exponential function of any base, the inverse is going to be the logarithmic function of that same base. So if my base is 10, then I'll have a log base 10. If my base is a, then I'll have a log base a. So this was a graphic approach or a visual approach. Let's see what we would have done algebraically. So over the last chapter, we've asked you to find the inverse algebraically of a given function. So you would have started by switching your x and y. So I would have written x equals 10 to the y, and then we would have asked you to solve for y. Now, if I try to solve for y, go ahead and try, right? We get stuck a little bit because we're not quite sure how to get that y out of the exponent position. So we need some more tools in our toolbox in order to actually figure out what the y is and in order to get it out of that exponent position. So we are now introducing some rules that we can apply to solve a situation like this or to figure out a situation like this with our logarithmic rules. So before we come back, we'll come back to this one in a moment. Let's take a look at a little simpler example that we are more familiar with, which is something like 3 to the x equals 81. We know that when we look at 3 to the x equals 81, that x is supposed to be 4. This is written in exponential notation. So now if I take this and I write it in logarithmic notation, notice your base for an exponential matches up with the base for the logarithmic as well. My exponent for an exponential matches up now with my answer to a logarithmic function, or equation, excuse me, and then your 81, which is your answer for an exponential equation, is now going to be your input into your log, which that's also called your argument. So anything that you put into a log right here, that's known as your argument for your log expression. So if I were going to read this out loud, since this is a little bit of new notation to us, we would read log base 3 of 81. So out loud, that would be log base 3 of 81. And what does that actually mean for us? So we know that if we have 3 to the x equals 81, we know that x should equal to 4. So let's take a look at the log notation now. If I have log base 3 of 81, I can rewrite log base 3 of 81 if I write 81 as 3 to the 4th power. And this is supposed to equal whatever my x is. Well, if I take a look at it written in exponential notation, it's very clear that my x is going to be 4. So where does that 4 come from in the logarithmic equation? I have the 4 right here as my exponent. So again, we have matching bases, which happened in our graph as well. Because they were inverses of each other, they kind of cancel out, I guess, is one way you could say it. But because they're inverses of each other, they'll reduce down, and I will wind up just getting x equal to 4. So in both equations, or 4 equals x, so x equals 4. In both equations, I wind up finding that x is equal to 4. They're just given in different ways. So if I think about this, and I go back to my inverse that I was trying to solve by hand, let me see if I can apply the same rule. So if 10 is my base, I'm going to say log base 10, and then of x is equal to y. And now because I've solved for my inverse, I'm going to denote it as the inverse of the inverse of f is equal to log base 10 of x. So all I've really done is use that same rule that we just applied to switch from exponential notation to logarithmic notation. So in summary, what I'm really looking at here is this rule where if you have any value, like we'll call it b, is equal to a base raised to the x power, so an exponential, I can rewrite it in log notation as x equals log base a of b. And we're going to talk a little bit more in class about why your b and your a value are going to have to be greater than 0. And then on another note, when we notice on the right-hand side here that base 3's matched up, so we have log base 3 of 3 to the 4th power, you'll notice that it reduces down to just x. So similarly, if I had a base a raised to the log base a, that would also reduce down to x. So anytime that our bases match, we'll reduce down to x, just our exponent, or your argument if it's in log form. So now that we know that when bases match, I can just take the exponent. Let's see if I can rewrite these following my hint. Let's rewrite these with base 10 because you're given log base 10. So 100 could be written as 10 squared. All right. And log base 10 of 1,000, we can rewrite that as 10 cubed, and so on and so forth. It's a great time now to pause and see if you guys can write these up on your own. Log base 10 of 10 is going to be 10 to the 1st power, okay? So we know from the rule that we just described that these should all equal just our exponent. So let's take a look at what our calculator can do to support us in this. So using our calculator, we can find log when we press Control and then the exponential 10 to the x button there is log, and it sets up a position for your base and your argument. If you don't put in a base and you just go straight to your argument, your calculator will assume base 10 because it's a common base that we use. But I'm going to put in 10 for now, and then our first one was argument 100. And we'll notice that we get 2. Let's try that one more time with log base 10, and let's put in 1,000. And we get 3. So coming back to our, this supports us in noticing that this is going to reduce down to 2. Log base 10 of 10 cubed will be 3. Log base 10 of 10 to the negative 1 will be negative 1. And log base 10 of 10 is just 1. So therefore, anytime that we have log base 10, so again, when there's nothing written there, we always assume it's 10 because it's a common base. So log base 10 of 10 will reduce down to just the exponent, all right? And that is for any real number x. So we've seen it now with different numbers, and we can now do it by hand and with the calculator for base 10. So there will be some questions for IB that you'll have to simplify these by hand without using your calculator. So again, you just want to make sure your bases match when I'm simplifying by hand. So a few examples that we're going to try to see what the different rules that we just went over, how they are applied. So first of all, I'm going to notice that there's no base written, so this is going to be base 10. So I'm going to try to match my bases. So 10 is just 10 to the first power by cube root of 10, which is 10 to the 1/3 power. Since I'm multiplying bases here, I can rewrite log base 10, and this can be written as 1 exponential. If I remember my indices rules and add 1 plus 1/3, so 1 and 1/3. And since my bases match, I can take the exponent. So I can simplify down log base 10 of 10 to the 1/3 is really just going to be 1 and 1/3. For the next example, I want to rewrite 1.5, I'll bring it down here, as an exponential with base 10. Well, if I write anything with base 10, in order to write 1.5, I'm going to use a base 10 and a matching base for my log. So I can write that 10 there, or I don't have to because I'll assume it, of 1.5 as my argument. Because again, if I have 10 raised to the log base 10, my bases match, and those would just reduce down to 1.5. So I haven't changed the value of this problem, I've just changed the way it looks. So I'm going to use my calculator's help to figure out what is log base 10 of 1.5. This time I didn't put a base in, just to show you that we will assume base 10 if you do not enter a base. And we'll take 3 significant figures, so 0.176 or 176 thousandths. And now I have actually written my 1.5 as an exponential with base 10. So let's just go back to our calculator and double check that it actually does equal 1.5. So 10 raised to the 176,000. Since I rounded off 0.176, I'm going to push Control and copy my answer, just so I have the exact amount, and it does wind up equaling 1.5. In number 3, I'm going to use my rule for changing from log form to exponential form. So again, I'm in log base 10 of x equals -5. So I'm going to say, changing to exponential form, 10 raised to the -5th power equals x. So I have solved for x. I could also write x as, if it's 10 to the -5th, I could write it as 1 over 10 to the 5th. Okay? Either way, just rewriting it in a different form will solve the equation for you. Writing a logarithmic equation for 4 cubed equals 64. Again, I'm going to match my bases. So base 4 is going to become log base 4. My argument, which is my answer, is 64. And then 3, my exponent, would be my answer for a logarithmic equation. So 4 raised to the 3rd power equals 64. And our last example, if you're asked to find log base a of a to the n, 2 ways to think through this. The first way is, since we've been talking about matching bases, I know that my bases match, so I should wind up with n as my answer. However, to think through a couple of the rules that we've done today, if you have log base a of argument a to the n, what you're really saying is a raised to what power would equal a to the n. So think about how you convert from log form to exponential form. A raised to this power is going to equal a to the n. So that's another way of just reaffirming that that is going to wind up being n. So what you guys just found out is that log base a of argument a to the n should equal n. All right, guys, have a good night. Try a few of these on your own before you come to class so that you're ready to try some harder ones and start proving a few of these as well.